I think I should do this. You want to do it?
That's going to be too long.
No.
Taken away from my name.
Okay. Frederick's going to introduce himself.
That would be. I'm not done.
All right, it's about time to get started. This week's seminar, our very own, you know him, you love him, Frederick Simons, who will be telling us about 20,000 Leagues Under the Sea with a fleet of seismic robots.
Okay, thank you, Chris. It's a pleasure to be here. I'm here often. I've given a lot of seminars in my life, but this is the one I'm nervous for, so please bear with me while I try to stutter through it. It's not me alone, right? And it's not just mermaid stuff. I'm going to talk about earthquakes, and I'm going to talk about microseisms, I'm going to talk about volcanoes. And there's a lot of people that over the many years have helped and shaped my thinking and done some of the work. And for all of you whose slides I criticize, please be kind tomorrow, because it's easier to be a critic than to be a primary producer. So, if you need to leave, I'm going to give you the conclusions, okay? And actually, this is not the presentation. I have the better one. Hold on. I made the version that had proper clicking. Don't worry, it's just like the other one. Okay? So, land-based seismic arrays need to go to the oceans. And mermaids, you may have heard of them, are floating, mobile marine sensors that do just that. And they were designed to record earthquakes, and they're doing very good at that, and I'll tell you a lot about it. And what we are doing with that is we are imaging the interior of the Earth's mantle using seismic tomography. And the primary target we have had over the last decade or so is a very geodynamically active, possibly plume-rich region around Polynesia, thousands of islands that are underlain, possibly by dikes or plumes or conduits or columnar upwellings that feed them, and that is what we try to get a handle on the structure of. And so I'll be talking about the earthquakes we collected and how we do the travel time tomography modeling, and I'll give you a little bit about how we look at the waveforms and so on. And so all of that is traditional seismology, if you will, with some non-traditional instruments. Mermaids also record noise, the stuff that happens in between earthquakes, the stuff that isn't an event, but that is just the always going on infrasound that is present in the ocean. And we are studying that, and we are linking that to what happens at the surface of the ocean and how that generates a well-known source of seismic noise of the so-called Rayleigh wave type, which I'll dig in a little bit. And then I'm going to take a brief step away from mermaid, because whoever says Rayleigh wave in seismology also says love wave, and that's a different mode of vibration of the Earth. And we're going to briefly talk about how love wave type noise is generated also by the ocean, which was a 100-year-old conundrum that is no longer a conundrum because of the types of modeling that we have been able to do. And then I'm going to conclude in showing you some of the non-earthquakes, non-noise sources that are nevertheless omnipresent in the ocean, and that is submarine volcanism. And in particular, I'm going to focus on the largest eruption since Krakatoa in 1880-something, which was the Hunga Tonga Hunga Hapai eruption. And so for the very first time, we were, of course, in the ocean already, and we heard it. And I'm going to show you some of those records and then show you how we've been building ways to interpret those records, because there's some novel structure that we are trying to understand. Okay, so mission statement. The Earth is a geologically differentiated sphere of things on the inside. And its temperature, its composition is not homogeneous. And that is a revelation of the geological structure and the geodynamical evolution. And all of these heterogeneities affect ultimately how fast seismic waves travel, those waves that are emitted by earthquakes. They also, of course, cause anomalies in the gravitational field. And of course, they're also manifest as subsurface and subsurface topography. So if you want my mission statement for geophysics and why we should all quit what we're doing and get into it, is that we need to study all of these observables: seismic wave speeds, compressional wave speeds, shear wave speeds, elastic wave speeds, anelastic wave speeds, isotropic wave speeds, anisotropic wave speeds. We also need to study gravitational anomalies, the static ones, the dynamic ones that affect the mantle convection inside the Earth, the time-dependent ones that happen because the ice sheets are melting and the Earth's rotation and its flattening are changing. And then all the aspects of topography, the shape and the size of the mountains and the bathymetry and the crustal structure and the layers below it, which reveal all of the heterogeneities at the surface, but also the deeper underlying things. And then finally, of course, how all of that interact with the Earth and the oceans. So that's my comprehensive view of how we should approach the study of our own planet. I'm not going to talk a lot about scale dependence and spectral densities and correlations, but those of you who know me know that I work a lot on those things. It's just not looking at one thing, but also at how it relates to another thing and how it relates to itself in time and in space. Topography, shape of the Earth, right? The visible thing that you can see, of course, is with respect to gravity. This is a rendition of the Earth's gravitational free air anomaly, just for a pretty picture, showing you that by looking at the gravitational attraction anomalies from the known structure, we are seeing plate tectonics, right? We are seeing subduction zones, and we are seeing collision zones, and we are seeing transform faults, and we're seeing hotspot tracks, and we're seeing all of this structure. And so that's a subsurface view through the dynamics of how literally apples accelerate when they fall, seen from satellite orbits. And then finally, earthquakes, they're everywhere, but are they? Well, they're primarily on plate boundaries, as you also know from Geology 101 or 102 or 103. They're on mid-ocean ridges, but they are smaller and they're shallower. They're also in between continental collisions, and they're also odd earthquakes here and there in the middle of the plates. So, first there's chemistry, and then there is physics, and then when you observe it using geophysical tool, to me, that's when it becomes geophysics. The very, very basics of temperature and pressure is a question: how hot is it? Down there. Composition, what is it made of? And even if the composition doesn't change, there's phase changes that lead to contrast in material properties. And yes, there's magnetic and there's density and so on. I'm going to just wrap all of that in. All of that change into the Earth maps into seismic wave speeds that we therefore must study to look at the structure and the evolution of our Earth. So how do you measure a seismic wave speed? Well, there's about 5 ingredients. 1, you need a source of energy, and let that be earthquakes. They are sources. It's basically a bunch of energy released at a point in space and a point in time that makes it and makes waves, which make it to seismometers. Those are recorders of wave motion, receivers that display, record 3 components of records of displacement or velocity of acceleration of what the actual ground is actually doing. We've been at it for a long enough while that we sort of know what to expect in a general sense. We have built reference models. We have built background models for the Earth. Most of those reference models are one-dimensional, but they're also increasingly complicated, 3D, possibly a little bit more smooth around those reference models that we can use as starting models to look at what our observations tell us that surprises. So in order to compare what we observe and be surprised with what the reference or the background doesn't tell us, we need a way to model how the wave field propagates through the Earth. And from earliest days of optics through more sophisticated ways, through the current state of the Earth as practiced here in Princeton, we are able to model what we should expect for known earthquakes to arrive at known stations. And then the magic happens in the end, where we assimilate all those differences, all those anomalies, all those surprises that we have about what comes out of the Earth in terms of motion from earthquakes, and try to build a new model, and then that's going to have more and more three-dimensional structure, and that's the art and science of seismic tomography. Reference models, there are a few, but the main ones are one-dimensional things. So here are the layers of the Earth, the crust and the mantle and the cores. And in this inset here, in this graph made by Raj Molek, we're seeing the density, and we're seeing the shear wave speed, and we're seeing the compressional wave speed, and we're seeing various measures of anisotropy and attenuation, which are details. So to first order, the Earth is a layered set of shells with properties that tell us something about the wave propagation, the speed thereof, and then that is linked to elastic constants, to densities, and to material parameters of temperature and pressure. Forward modeling, this is what many in the room here practice, and that is these days done on supercomputers, but also routinely. An earthquake happens, like in Oregon, and wave fields are computed. We know enough about the Earth to solve the partial differential equations that tell you what the waves should be doing at 1 and 2 and 3 and 4 minutes out. And so it's hard to appreciate perhaps, but you're seeing things that aren't simply geometric anymore. It's not like ripples on a pond. There is already structure developing because we have crustal thickness variations, and we have wave speed variations, and we have an ocean, and we have all of these things, which this spectral element modeling technique actually does capture. And so as a community, we have become very good at modeling seismic wave propagation in the solid Earth, and including little bits, and growingly so, of its ocean and its atmosphere. So these are some of the routine things that you'll find on the Shake Movie website that the Jeroen's group and various people present are making for us, and thank you very much. Well, whichever the reference, whichever the background, 1D, 2D, 3D, something that is a little bit more complicated with respect to which we want to see the structure vary, this is an example of a record. This is a transverse component, so this is orthogonal to the way the directions of the wave travels, and one of the colors is a three-dimensional smooth background model with some discontinuities in it built in, and the other color is the observed phase, and when we look at specific portions of it, we are measuring the difference. And so here is the primary wave. It's not visible at this scale and at this frequency. This is the secondary shear wave. These are the surface waves. And so we zoom in on particular parts of the wave field to try and track if they're early, if they're late, if they're big, if they're large, if they are anomalously dispersed, if their amplitude is different from what we expect. So we make all sorts of types of measurements, but the primary one is literally when is this wave showing up, because that carries the history of the material that it went through. And then on the basis of those types of observations, we try to build better and better models for what the variations are of the wave speed with respect to the background model. Here's another example, another pass through the Earth. So, focusing on this particular wave train and looking at a detail thereof in the inset, and then you're seeing this one, and it needs to be adjusted a little bit. It's a little bit too big, it's a little bit too slow, and so by advancing it a little bit, you can incorporate this information. So that's the general idea of how we proceed as a community. We build a reference model, we solve the proper equations, we see what should come out, and then we look at how different it is. And at the primary stage, that's how early or late those things are. And then in the more involved stages, that's what their shape is, what's their phase, what's their amplitude, what's their dispersion, what is all the attributes that you can make to compare one thing with another thing, which is a time series of motion or displacement or velocity. And then we put all the information together, just like X-rays, if you will, in your medical, or like ultrasound in your medical technology. Except for us, so earthquakes are the sources, the wave propagation happens all over the globe, and the seismometers are the things that record that motion. So if we look at where we've come, we have imaged a lot of the Earth. There's various groups, and here is one example that is coming out of Jeroen's group, made by Ebru Bosdag, and a couple of iterations back. 400 kilometers a cross-section through the Earth. You're seeing Australia, you're seeing the US. Much of that stuff is blue because these are anomalies that show faster than average wave speed propagation, which typically means it's a little colder, it's a little stiffer, it's a little stronger. And red areas are areas where the material is propagating the wave speed, the seismic waves, slower than what the reference already predicts. And that generally means hotter than the average, and therefore less dense, and therefore buoyant. And so at 400 kilometers here in this particular model, what's outlined is various known things where stuff comes out of the Earth, the Galapagos, the Hawaii, Tonga, various areas where we know there's volcanoes that source material from the inside of the Earth. And here centered on this section is also the Pacific superplume, is essentially just a large region where there is a lot of stuff that looks like it's anomalously slowly propagating seismic waves, and therefore anomalously hot, and therefore buoyant, and therefore probably giving rise to what comes out at the surface in terms of volcanoes. Here's a couple cross sections here. This is from another one of the global tomography models from Jeroen's group. So this is GLAD M25. Here we're seeing Pitcairn, Louisville. This is the cross section through the Earth. So this is in the Pacific. There we're seeing Tahiti and the Marquesas Island. This is the particular cross section. This is a shear wave speed, basically just wave propagation. And red again is slow, and blue is fast. And so that which I previously showed to be the super plume, or some area of blobby material that looks like it's coming up in these two views. Now, this is not the only group doing it. Here's another group. This is from Barbara Romanovich's group, who spent a couple of months with us a year or two ago. This is the SEM-UCB model, and these are the same cross-sections, the same scale, and the same property, but with different modeling techniques, approximations, and data, and so on. And these are the left-right comparisons of the views of what we should start to take away is, well, first of all, there's definitely stuff down there, but also in various models, it's not exactly all converged yet. There's still differences. Model A in these two, or Model B in these two, whatever the remaining differences are, is part of why we're continuing to do the science, because we are not done. It's not the final answer. And I'm also not able to show on this scale what the uncertainties are, the pluses or minuses, that would help you reconcile these two views. So, when we talk about mantle plumes and upwelling and the large-scale geodynamic structure of the Earth, we are interested in what it means geologically. And if we just take 1, 2, 3, 4, 5 different sort of mental pictures of what a mantle plume is or could be, we're not sure if all of them are anchored in the deeper mantle. Maybe they're superficial features. Maybe they're actually set up by plate tectonics rather than large-scale mantle circulation. Maybe some of them hit particular contrasts, like these famous discontinuities that are phase changes that reflect waves but also deflect motion and that lead to ponding and maybe rising up again. Maybe they're straight through columnar upwellings that are, very efficient conduits of material. And maybe there's places where something happens that is either impeding the flow or a combination of, models, or maybe we just don't see it. And for us to pick up a rock from a volcano and think about where it came from and what properties and information geochemically, petrologically it carries about the inside of the Earth, we do need a 3D time-resolved view of where that material is coming from and how it's going, and basically what the mantle plumbing system is, in order to understand what we can sample as rocks on the surface. So why are all these views different? Why are these questions? Haven't you spent long enough, on this problem community? Well, there are just never enough earthquakes. And of course, every one is a tragedy, but we are generally needing the sources to give us the energy that can be propagated and compared. And while we have thousands of seismometers and multiple channels and 50 years of digital everything, is never enough seismometers. And in particular, for the imaging of mantle plumes, that leads to some fuzziness, to some uncertainty. I like to say it's especially true for mantle plumes as opposed to the downgoing parts of the convection system, which are the sheet-like subduction zones that carry stuff from the surface to the bottom. The reason is that slow wave speeds tend to deflect the wave field away from it. They are unlensing, and therefore they steer away and around it, and so it's a little bit harder in general to image low velocity contrast than it is to high velocity contrast. That's a basic of wave propagation. So how bad is it, doctor? Well, we have lots of good stations. These are some high quality stations. Most of them, of course, are on land. Some of them are on ocean islands, and those are pretty noisy because they're being shaken by the waves of the ocean, in addition to the seismic waves they capture. And in vast stretches of the ocean, there was essentially nothing. So, more years ago than I should comfortably admit to, Argo, the oceanographers, were building a worldwide network. And this is 2 days ago. The state of where the oceanographers have floating equipment in the ocean, okay, everywhere. And that is part of the Argo program, which samples properties of the ocean water. And so back when I started here at Princeton, we knew this was coming, and we're like, we got to do something for seismology. We have to capture some of the solid Earth signal while these oceanographers are out there. And in their great collegiality, they said, no, don't get lost. We don't want to carry any recording devices on their oceanographic program, because that leads to all sorts of complications with legal stuff in the Navy and whales, and also they just didn't have the bandwidth for it, literally. And so we took inspiration from it, but asked ourselves, can we build something like this that is, the same idea, instruments that are autonomous and going places, for seismology, so that we can conquer the ocean without going to the bottom of the ocean, which I might have mentioned. There is ocean floor seismology, which is very good, and all sorts of great sciences coming out of, but it's very limited because it's very expensive, it's very hard, ships are expensive, and it turns out the ocean floor is deep, and the water is heavy and wet, and so it's really hard to go to the ocean bottom with proper equipment, or even get the equipment back sometimes. So that was our mission, to record teleseismic earthquakes, distant earthquakes that were suitable to improve mantle tomography. That's the goal that we set ourselves. And so MERMAID was born, Mobile Earthquake Recording in Marine Areas by Independent Divers. And the acronym, by the way, is coined by Hugues Nollet, who some of you will remember. So I talk about phases, think of earthquakes, right? An earthquake and a station, and when it's local, it's no good because it doesn't go through the mantle, okay? It goes a little bit through crust and maybe some water, but those are not the ones we want. When I say teleseismic, I mean, well, it's got to cover some arc across the globe. It has to be distant enough that through the nature of wave propagation, that the wave path, this whole wave field sort of samples directly the interior of the Earth's mantle. I'm going to also point out a few core phases. They go through the core, okay? And there is a whole aspect of core seismology that is, among other things that Jessica Irving was interested in, that requires some novel sampling, and we do get some of that as well. So, brief history of MERMAID. That was the one. We went to the Scripps Institution of Oceanography and bought an Argo float of the solo variety, and we equipped it with a hydrophone to record acoustic waves generated by earthquakes, whichever. We didn't know if we would get any. And in fact, I did get one, okay? And that's the one, my first one. You do never forget that. And so this distant 50 degrees across the arc of the globe, so about 5,000 kilometers away, it's magnitude 6, so this is a healthy, respectable earthquake, a global earthquake, came up and sounded like this in the middle of the ocean recorded by a free-floating solo instrument. And that's what it is. And it was expected at 0, and that's what it came. So the reference model is subtracted out here. I'm going to fast forward to, we needed a bigger one, and we needed more, and we needed autonomy. And so that's when, briefly, all of this development changed, and they made it longer, and they changed the color, but essentially it was still a microphone in the water that was autonomously going, doesn't steer itself, is never recovered, so no ocean ship time, and just autonomously reports earthquake waves using algorithms that we built that are part of another story. So these particular ones, only 11 of them were built, but they were tried in various places in the Mediterranean because it's shallow and close by to where they were deployed, in the Indian Ocean. So these are examples of unfiltered, so you see the noise, P waves like I just showed you. These are some core phases coming out, so having propagated through the cores, and basically a whole variety of teleseismic events that showed that this could be done. In addition, there also was a lot of unidentified earthquakes, because it turns out that because the dearth of stations across the ocean, you were in the middle of the ocean, nobody literally has heard there anything ever, and whatever it comes out includes, in this case in the Indian Ocean, 250 some earthquakes that were not on any map because they hadn't been heard by any other stations. They were just little, and they were therefore not recoverable on anything else. So I'm going to make that the side story here, local little earthquakes that told you they don't help you with the mantle imaging, but they surely help with tectonics and with plate deformation and with seismic hazard and risk. And so that's sort of I call that the bycatch of Mermaid. And so there we went to the first scientific target, and this is the one slide I'll show of what we found when we looked at the mantle structure using all of this framework in the Galapagos Islands, which are, there. There were only 11 mermaids launched, and they only had a lifetime of 2 short years, and they didn't go where we wanted to go. We wanted them to do a nice array around Galapagos. Every one of them is the same one, but there's 11 different colors here, but they're just popping up at random times when they record these earthquakes. But so the collective array that you get after 2 years, what we wished for was something that nicely circulated the target so that we had an aperture of an array that seismologically would do something with. And yet, they sort of went wherever they went, and we sort of missed all sorts of things. But it was enough. It was enough for a science target. It was enough for a science study. And it was enough to produce these pictures here. These are 2 cross sections. This is one along latitude. This is one along longitude. And I'll just look at this one here. And now you have to use your imagination, right? And then later on your interpretation. But so they're centered on the Galapagos main island. And so you want to see, again, the slow velocity anomalies that show structure. And that one, if one then does further modeling, can try to interpret in terms of, what's feeding the surface expression in terms of surface volcanism that are the Galapagos Island. So we did go around with this as, a success, but of course, these mermaids literally were little, and they were literally only deployed, 11 of them, for 2 short years, and so we did not have the full-scale experiment. So we realized that we needed to go 3G, okay? So we went and built a 3rd generation mermaid. It's bigger, and because it's bigger, it can carry more batteries. And so this is a glass sphere. This is a standard rated 6-kilometer sphere, inside of which there is all of this electronics and these algorithms, but also mostly batteries. To give it its autonomous buoyancy, it pumps around the hydraulic fluid, and it slightly changes its density and therefore goes down or goes up. And we control that, but we don't want it to be fast anyway. We can make it faster anyway. So a little bit of buoyancy and it goes down, and a little bit of buoyancy and it comes back up. This instrument was rated for 2-kilometer dives, and we bought it, designed, then bought it, to be able to do 250 surfacings down to 2 kilometers, where it would just listen and report earthquakes when it heard them, and then come back and do that. Iridium for communication, which, by the way, is 2-way. We can talk to it. GPS, which is, by the way, not just for location, but for time. I talk about speed all the time, and so we need to know where the station is, and we need to know very well what the time is, because we're looking at subtle variations of wave speed propagation that could be measured in the fractions of a second, and so we really want high precision timing. Anyone of you that's ever deployed an instrument anywhere knows that clocks are bad until they get expensive, but you can reset them using GPS, and so that's in fact what we do. Every time the instrument comes back, we're like, okay, just do the time correction so you don't lose your precision as you go along your trajectory. And that's the trajectory, right? Put it out, it goes, it takes its sweet time. We program it to sit at a program depth, and this you got to think about 2 kilometers now. And then it just listens for everything, everything. Now and then there's a good earthquake, and then it's going to speed up, report it, and then go back down. We can also pass it a message which usually is, good job, go back. But sometimes it is, give me a little more, stay a little bit longer, go a little bit deeper, call me. Those are the words we whisper. Okay, so where is Mermaid? Well, it turns out in the move to the building, the firewall prevented me from showing you the latest map, so this is from before the move. But I'm going to get that fixed, they promise. This is, ultimately, we formed a consortium, went around with the Chinese, and we went in the sea with the Japanese, and we went to the Mediterranean, but most of what I will show you now is from the array centered on Polynesia, because that's where we're mostly targeting at first. Travelers might recognize this as the island of Moria seen from Tahiti. And seismologists will recognize this from old models where, you know, here again is a 1992 model by Yoshio Fukawa, a pioneer in tomography, who showed the underlying slow, presumably upwelling, presumably buoyant, presumably hot structure that somehow or other seems connected to Tahiti, right? I don't know what the pie chart really is about, but that's the core. And so the colors here are the mantle velocity anomalies, again in the same slow to fast wave speed. So then it makes into geology textbooks and in petrology and geochemistry and geodynamics interpretations, and then something looking like this on the left makes it into something like that, where there's a cartoon that says, yep, there it is, this is the upwelling, and that's the sort of general idea that we had. But that's 1992. If I look at the Romanovitz models, I showed you one earlier. This is by a guy named Scott, French, 2015. So these are 2 cross-sections now. Again, look at Tahiti, right there, this way, and then a little bit that way, but I'm going to look on the right here. And so with some imagination perhaps, but we're seeing this more detail of this upwelling structure. We're seeing that it fingers, it branches, it comes out, and so we're seeing more detail with more modeling, but we shall never forget that this is still thousands of kilometers, and this is the high resolution work that we can do. This is great modeling, but it's ultimately relatively long period waves, relatively smooth views through the mantle, and so we look at it inspired, and this is what we're trying to improve upon. So lack of data, bad. 60 mermaids every week reporting a new earthquake from a new location gives you an array that, once again, it didn't quite go in a beautiful circle, but these are all the surfacings, 7 years. I told you 250 surfacings, but it turns out about once a week it reported an earthquake. We thought it was going to be 5 years, but it turns out that 7 years, and now they're dying, okay? So we went in 2018, and we've continued collecting, but we've sort of stopped about now, and that's the picture of where every one of them, you see individual traces here. This is one mermaid reporting all of these earthquakes from these locations. So for every surfacing, you got to imagine it collected a whole new wave path. Many, many earthquakes, shallow ones, deep ones, intermediate ones. And so after all the careful analysis that primarily here, and I'm going to call out Joel Simon, who is not able to be here, made all of these measurements on all of these little bits of records with an earthquake coming in a little waveform. And this is the latest bubble plot 12,000 travel times, 4,000 earthquakes, 61 mermaids around the Pacific, and every one is on magnitude of earthquake versus epicentral distance between 0, which is right near, and 180, which is antipodal. And you're seeing we've collected the world's earthquakes over these 7 years. Of course, not in the gaps given by the core, shadow zone, and so on. But so this is a signal-to-noise scaled version of where every observation has been in an area where we had literally never listened to any activity of seismology of any kind from anywhere. So we are doing this now, and we're going to look at travel times. So here's a little record of an earthquake, and I'm going to talk about the ups and downs. Then I'm going to talk about what the reference Earth says. Oh, the P wave, the compressional first arriving wave, should arrive here. An automated algorithm called F says, start looking here because it looks like the wave is coming, and then more careful analysis shows and is interpreted, that's where the actual wave is arriving. And so in the very, very high frequency, old school ray theoretical viewpoint, we're measuring this as this difference of, that's the delay that we are seeing, and that's the sort of primary data that we invert into these models. Now, because we're doing regional work, we do embed it into a global model, and so ultimately we have 11 million arrival times from 40 years of catalogs, to which we were adding 5,000 and a bit of these high-quality mermaid records in this area, which never before really had any sort of good data. And so I'm not going to discuss the whole model in that much detail, but I do want to focus you on the target at a few depths, at the traditional color scale, where the redder, warmer colors are slow velocity, less dense, hotter, presumably buoyant. And so if we descend into the mantle at 300, where we still see the evidence of the continents, then we're going down 500, 600, 1100, 1800, and around 2700, when we're near the core, we seem to be losing the signature of the system there. So this is still in review, and it's only based on travel times, and so a full interpretation is lacking. And what you all are asking is, well, can you go beyond just measuring the arrival times? And the answer is yes. And those of you that have witnessed Ivy's defense know that we're able to actually do the full waveform modeling, but the model I just showed doesn't have all of that in there just yet, because we have just figured out how to do this waveform modeling. So I'm going to go show you just 2 slides. If we take into account what the waves are doing when the ocean floor gives way to the water, and we look at the details of the bathymetry, then nowadays we are indeed able to predict, there's 2 traces as a function of time here, the actual shape of the waveform. And so we are now in the business of actually measuring more broadband travel times, more cross-correlation travel times, more waveform-based differences, and so on. So we're collecting a whole new set of data on these measurements to incorporate into these latest kinds of modeling, which the previous model was not based on just yet. So that is what we've detected in terms of earthquakes. We're doing Polynesian plume topography to try to link it to the geodynamic evolution of the Earth. We're going to do more of it, but I need to now do my detours. And one is, well, we don't normally recover it because we just report a signal. But Lucas here recovered one of them that had been in the ocean, had done this whole path, and because it had a whole year of data, much of which important stuff was reported, we just read the entire data buffer and looked at the stuff in between, which is just noise. Just to give you a sense of scale, this thing, which is a year's trajectory of a mermaid, is like fitting in this box. It just shows you how big the Pacific really is. And so now, instead of just the little bits of P waves and that we model for the little details of it, we just basically have a long record. And you're seeing all sorts of structure. And what we're, of course, seeing here in the center is this band of power. So this is time, and this is frequency, and the color is intensity of the signal or noise that comes up. And that noisy, noisy, noisy band is non-earthquake related. It's made by the ocean. So what's the ocean surface doing? Well, you look at what oceanographers model with their instruments of various kinds and with their modeling and their hindcasting, and they tell you that if you look at the ocean at this particular point in time, 0 hours, and then 6 hours later, and 12 hours later, and 24 hours later, you're basically able to ask the oceanographers what, based on their observation and modeling, the ocean was doing. And much of how to look at what the ocean is doing in terms of interaction with the solid Earth, we owe to this guy, whose name is Klaus Hasselmann, and who shared the Nobel Prize in Physics in 2021. Seen here, looking at the ocean and at spectra of waves, his mechanism, and there are others, help us predict what the power spectral density is of the ocean noise that you can hear in the ocean and feel on land. Nobody was hearing it in the ocean except us now, and so this is our records of that year in the Pacific. This is just a week in whatever, January. And so frequency is on this bottom axis, intensity is on the top axis. We collect here, we cut it off here, so you're seeing this go down. And so the shape of this curve is non-generated by earthquakes, not generated by ships, not generated by whales, not generated by anything else. And the intensity and the variation of it with time is a reflection of ocean state, which we understand thanks to the theory developed in the 50s, 60s, 70s, 80s by the likes of Hasselmann. So if we make the mermaid observations go on the y-axis, frequency of those, and then the ocean wave modeling on the x-axis, and we listen to the Hasselmann and others mechanism, then there should be, along the 2-to-1 frequency line where you double, there should be an explanatory, oh, it's the ocean waves making the sound waves relationship. And where that relationships hold, the coherence is high, and that's red here. So this is part of Ivy's work also, showing you right on that dashed line where we expect the coherence between what the ocean waves are said to be doing and what we can hear when we're actually in the ocean is great. So here's an example of that point there. See, very, very highly correlated. Now we're just filtering it a little bit, and it shows you over the course of an entire year, hour by hour, in fact it's every 3 hours, that when the wave stays high, the noise is high, and when it's low, it's low. And the correlation over an entire year is just really, really, really good. So what does that mean? That means that Mermaid observed something called the secondary microseism generated process in situ. First time that there's all of these recorders actually literally in the water column hearing this mechanism, which we knew coupled the ocean surface to the ocean bottom, which was audible on seismometers, including the one that, if the room gets finished, we'll put down in Brigger Hall. That's the first thing you hear, is the noise of the ocean. But so now we have a way of, while collecting earthquakes for tomography and for doing interior of the Earth, solid Earth imaging, we have a way of listening to the ocean, because I showed you high correspondence of the ocean models, but that's also based on observations, and that's also not perfect. And wouldn't we also like to have other ears on the ocean state? And this is one of those things. And I'm not even mentioning that if you do this for a very, very long time, like we've done with seismic land-based records for 30, 40 years now, that we're actually hearing the ocean warm. And that, if you remember the talk by Rick Astor, hello Rick, who talked about the slow intensification of ocean noise, because as there's more energy in the ocean, the wave state and all of that is just slowly rising, and we're, in other words, having access to another environmental sensor. I'm looking at the time, and I'm going to skip over the next question, but I'm just tell you how important it was to also look at that, and I'm cutting it out because it's mermaid, non-mermaid related. I told you if we can hear this noise of the ocean waves, which essentially basically like going up and down, and we can hear it coupled to the ocean floor, but we're now hearing it in the middle of the ocean, and that's motion of the Rayleigh wave variety, which is essentially sort of dominantly vertical pounding and compressional type of structure. Then I told you that there's going to be other waves of transmitting motion. You know it. Shear waves are transversely polarized, and so the equivalent to a Rayleigh wave, but for the transverse direction, is a love wave. And it literally was not clear at all how the heave of the ocean that's the fun part, how the heave of the ocean could produce sideways transversely polarized energy in the seismic record. And so I like to say, how does the heave of the ocean produce sway of the Earth? I'm not going to give you the detail. I'm just going to tell you that when Lucia Gualtieri was here, we, Jeroen, Etienne, various people, worked together on, first of all, trying to find the transverse component from a record that's just made a noise. Then use the ocean models to see what the source driving would be as a time-resolved spectral densities of what literally the oceanographers would tell you the ocean is doing. And then try to model it using the SpecFEM 3D package to try to simulate the entirety of the wave propagation in order to find transversely polarized love waves. I'll skip over the technology. I'll just tell you, if the Earth is 1D and has no topography, that's impossible. You cannot push up and down the Earth and generate out of the plane motion in terms of shear waves or love waves, rather. And so you find nothing. But if the Earth has bathymetry, which of course we know and we study for that and other reasons, and the Earth has interior structure, which of course we know, and that's what we're all about trying to find, then we have ways of converting that wave heave of the ocean water waves into different modes of wave propagation, including filling all of the modes of how that really works. And then you can generate shear polarized surface waves called love wave. I'll skip over the technical detail, how to do it, but if you look at when you're done at, say, a station, and you're doing all this processing, and you're identifying where that transversely polarized noise sounds like it's coming from, then you get a little histogram that points to somewhere. The background here is the ocean wave state, one snapshot, one time, one frequency. So anyway, this station, that station, that station, that's the love wave generated noise. If you point all of that to where that's coming from, then you're seeing that all these stations are saying, oh yes, that's right, that's the source of that noise. It's not perfect, but of course it's all noise. So what this is saying is that if you're looking for this transversely polarized love wave variety noise, then once again you're hearing C state. And we didn't literally previously know mechanistically how it all worked until we did this sort of modeling, which therefore concludes by saying, well, ocean pressure does generate this type of noise. And that's primarily via interaction with that 3D structure inside the Earth, where wave conversions can happen in the solid Earth. And yes, there is a little bit of bathymetry that helps you transmit that motion, but it's really actually majorly by the 3D structure of the Earth. And so that's yet another reason to want to know about the structure of the interior of the Earth. Okay, I'm going to conclude and go back to the long, long records and go, we talked a little bit of P waves and we did tomography. We talked a little bit about a noise, which ends up being of the Rayleigh wave variety, and that tells us about C state. And I skipped a little bit over the love wave, which tells us even more about the Earth and the sea. When Ivy and I looked at the 1-year record, there were also long stretches where there were no earthquakes and no ships and no whales, but nevertheless bursts of energy. This is time, this is frequency, the color is intensity. Similar view, but this is frequency, this is intensity over all of time, and you see that spectral shape again, which we study in detail. This is in the time domain, so that's literally the sound of the ocean, and this is filtered in a different bandpass. And so you're just hearing stuff. And we wrote that paper in 2022 saying that's probably submarine volcanism, because that's the other source of transient noise in the Earth. Then, of course, Hunga Tonga happened. And I rushed to the roof of Geo Hall to look at the barometer. Well, in fact, it was all digital and it was already on my desk, but look at the air pressure on the roof of Geo Hall. Right there, do you see that? That is the blip, one of the blips, of the explosion when that volcano literally blew its top off underwater, which coupled into a water wave, an atmospheric wave, a tsunami, and so on. And that's when it shows up. You know, Hunga Tonga to Geo, 12,000 kilometers, there's a short way around, 27 the long way around, and then multiple more times. So here's that one blip. So I sent this record to Stefan and Gabe. I reread your response email, which was, well, shrug. So what? You heard it. Anyway, then I went to requesting all the data we could from the mermaids that were in the water, because they're just reporting earthquakes. We tell them don't come up for submarines, anything, noises of non-earthquake variety. But some 24 of them were right there at all distances and azimuths, and we queried those records with the two-way communication, and we're like, hey, just give us another hour. Normally, we just give like 5 minutes because it's expensive to recover the data, because you have to pay for the bandwidth. And so we're like, okay, 24 hours, because what is the nature of this volcanic eruption? Because we were right there hearing it. Took a while, also took a while to write the paper. It's just about ready to come out, I guess, depending on the revision. But let me just give you a 2-minute example set here. This is one mermaid hearing what's called a tertiary wave. This is the sound of that volcano. And so there are peaks, there are things that other people have looked at. There is a long rumble, so there's a variety of phases in this eruption which ended, you know, started with a couple bangs and then sort of ended in a rumble. That's the time domain. This is, again, this frequency time domain, so this is time, and this is frequency, and the colors now are intensity again. And so you're seeing, whatever, the time frequency signature of that pulsed event of this volcano going literally boom. And so we have this record, which is an unprecedented set. And the ones on the left are all mermaids, and then we also captured some from the international monitoring stations, the ones that are listening for nuclear explosions. And the blue ones look alike, and the black ones maybe, and the gray ones not so much. So, Mermaid 45, record section time since the eruption, epicentral distance across the surface of the Earth, so we have a lot of them. This red one looks like that. 23 looks like that. Very similar looking. Different distance, same azimuth. And if you chop them to pieces and glue them back together and then shift them by the time it takes to go from one to the next, the top one is one, the bottom one is another one. And what you're seeing is that these two records look exactly alike. So that sound in the ocean made by this volcano was heard twice, and the signature didn't change. 49, the irony, I suppose, heard nothing. 48 heard the same as the others. Why did one of them, perfectly working instrument, not hear a thing? Well, we're in different places. This is one, a pair here, that was at the same distance, so that's not part of it, but slightly different azimuth and doing slightly different things. So among the questions that we want to answer is, like, well, how directionally is the output of this volcano? How much possibility is there that actually by looking around the angles around it that there's different energy inputs into it. In the end, we had to reject it, and we started modeling, and this is where I'll be ending. We looked at the dominant influence of the propagation path. So now what we're looking at is along the path between Hunga Tonga right here and the Mermaid, this particular one which heard it. This is the transective ocean bottom topography that it had to propagate this acoustic wave through, and you're seeing an example here where multiple times the topography pierces a line drawn at where the majority of the energy is actually being propagated. And then when we put our eye looking at the horizontal plane here, now this is the distance from the Great Circle path, which is that line, and the distance from the source again. The colors here are now, again, the ocean bottom, the ocean floor elevation. So what we need to do is we need to sort of count and quantify and understand the interactions of this water wave, which doesn't tell anything about the solid Earth, except it seems to be scratched at the various points by the ocean floor topography. Of course, that was to be expected, but what we developed and looked for, this is again the work of Joel Simon, just about ready, I hope, very soon to be published, where we developed a way of counting the interactions of the ocean bottom with the hydroacoustic phase. And so the takeaway here is it works pretty well. We can explain, taking into account the distance, taking into account the geometrical spreading, the remainder of the structure as however many times on a log scale in a particular counting scheme we developed, it has interacted with the ocean bottom, because that explains the sound level pretty well. Of course, they're scattered. Why we, of course, want to know these things is because any sort of analysis of any underwater mechanism needs to have records that are understood in terms of what signal and characters they have. I briefly mentioned the International Monitor Station for Nuclear Explosions. They're put there because they want to guess where the nuclear tests are happening and how big they were, the yield. But they need to know how far that sound travels and what energy it loses, because it turns out that is an enormous amount of energy that it loses depending on the path it took. But the path is not the same, and so sometimes, like 45 and 23, you lose nothing because it's a deep ocean with little topography. But sometimes you got to cross all sorts of structure, and then you're sapping the energy because it leaks into the solid Earth. And so we arrive at calibration curves of how to read ocean records for long path propagation to understand mechanisms such as volcanoes and other things. And that's it, really. We heard a lot of earthquakes, we heard a lot of noise, and that's good for the ocean. We also heard a lot of submarine volcanics, and that's, best illustrated with Hunga Tonga. And the heard signal is strongly influenced by path effects more than anything else. So, told you could leave. We need more stations, although Mermaid is not a station. I always fight the word. It's not a seismic station, it's a mobile marine sensor, because it's never in one place, it's not stationary. We record earthquakes, we're modeling that to understand the structure of the Earth and to link it with what the inside of the Earth is doing in terms of structure and evolution. I showed you an early model which is based on these arrival time peaks. It took a long time and it is well done, but I think the next generation is really going to do this proper forward full waveform modeling, and I'm looking forward to being here a while and working with you all on that. Mermaid records noise. That tells us something about the ocean, not the solid Earth. We understood that. We were expecting it. We had a mechanism to probe and we observed it. Then we took a detour in the parts of that record which we didn't understand nor had Mermaid observations for, but we did a modeling study to understand that transversely polarized love wave noise. And then I ended by saying, look at all the other stuff we're hearing. How many underwater volcanoes are there erupting? They are not all producing land waves that are recordable on GeoHall. By the way, that station is down. And in order to quantitatively study these strange sources in the ocean, we need to model that wave propagation. And that's maybe traditional types of modeling, but also simpler things that help us understand how the oceanic propagation path of a hydroacoustic sound wave is interaction with the ocean floor. And then that is why in another 15 years, I suppose I need to be back here to tell you all the work we're doing on looking at the ocean floor. Positioning with the seafloor geodesy, looking at correlation structure, looking at the stochastic nature of that thing, because not everything is directly observed, but literally that's for another day. And that's also for another day, only if you ask about it. Because it's 1:15, I'm looking at the clock. None of you are, but I am.
We'll have to go teach, but I'm sure Frederick will answer any questions anybody has.
Wenchan.
So all the topics, especially our topics, there are like activity from the ocean part, like that. Do you think it could be like the steam from the records from warming?
Yeah, we have all sorts of plans to look at ocean-atmosphere interactions, but all my calls to NOAA were not returned. So we're just collecting the data, and then there will be sufficient scope to look at ocean modeling and atmospheric modeling because, you know, in between the earthquake, we hear a lot, and right before the earthquake, we have records. And so if you have ideas for new things to hear, including longer cycles, because we've been at it for a while, we're sitting on data that we haven't even started analyzing.
You have multiple slides showing like your recent result of tomography of a snap seems to disappear at a certain depth. Could you tell a little bit more about it?
Well, so I didn't get enough time to make proper cross sections because this is a developing model. What I did show you ended around 2,600 kilometers, and the ocean core mantle boundary is, you know, is very nearby there. And so what I showed you in terms of the still localized anomalies that are going down, it looks like that's a whole mantle signature, which we also were expecting because, you know, those early tomography did show that, but we're imaging it with new data for the first time with all these new records and then embedded into the global models, and we're still in the phase of interpreting, comparing, and the paper isn't quite ready yet. But so we are reading, this is the best it's going to get at this point, because this is now the latest data set. Although other groups have now started putting ocean bottom seismometers on, and I'm looking forward to seeing what their records are and how we can make it even better with new observations. But so the first order structure is that, yeah, it's a strong anomaly that persists down to almost the core mantle boundary, and that we're going to look at what the precise 3D structure of it is in order to make better interpretations of it.
So you showed the big agreement between the wave model and the noise that you hear. Is there information that could constrain further what we have? Because from wind and wave model, we can get, I think, a decent sense of what waves are doing in the ocean. It's not perfect, but do you think there is a way to constrain more with that, or it's just like,
Well,
what are the type of things that we could be constrained?
Well, I'll tell you one other type of thing I could use it for, and that is to understand how we hear certain earthquakes of certain magnitudes and certain distance, because we have to hear them above the background made by the ocean. And you're all not always available to tell me what the ocean noise is, and even that WaveWatch model is backwards looking. It's a hindcast, right? It includes, you know, and so in places where there is no oceanographic observations or modeling, or not yet, we could use the intensity of that noise to help us with, you know, detecting earthquakes and looking at that sort of stuff. But I'm also thinking that imagine an entire agency were to disappear that does ocean modeling and observation, we'd be still hearing something that we could do. We can understand that part of the record in the absence of ocean observation. And then those of you who remember Thomas Lee here, understanding for us what that mechanism is, helps us understand what the historical record is, because we go back 100 years before there were ocean observations, and helping that is another part of why we need to understand these things.
That was my question. Is there a way, because with the mermaids, no, but is there a way, some of those were land stations?
Yeah.
And so is there a way to go back in time and
And the answer to that is yes, and that is what some people are doing, and that is what this sort of knowledge contributes to quantitatively understand what ocean-atmosphere interactions and solid Earth is doing when you have only land-based records or only ocean-based records, or in other words, non-oceanographic. It's another way of studying something that we're excited about.
So I want to push it for you to say something more about the image you did show of the seismic velocities from the new data. It looked like there are sort of fingers reaching up from some larger low velocity region to each of the major volcanic islands.
It had already looked like that. It still does look like that, correct? In your look at it.
Yeah.
So this is the sort of thing that we need to look at, right? So first we got the data, then we make the model, then we test it, then we do the resolution test. So this isn't quite done. But if all of this was what it is, that's what we'd have to explain in terms of buoyancy and density and temperature.
Does this scale of heterogeneity sort of make sense, or does it introduce new questions about the rheology of the material?
I think a fair question you might ask if this is actually, well, let me just try to answer your question. I don't think we have found an entirely new small scale of things. I think that scale was always there. We, in our sort of travel time modeling, come a little bit rougher than people in the full waveform modeling community with whom we are converging, but they're sort of in the smooth variety and we're in the probably overly rough variety, and somewhere in the middle is probably where the truth lies. But it's not like any of it so far has led to us saying like, oh, there's an entirely new thing going on. This is part of the scope of models. I'm not going to show you the comparison with 3 or 4 other global models, but they all look different, and we need all those vantage points to try to make collective sense of it, but they individually look somewhat different, and that's our challenge. None of it is perfect, even with new data and ongoing modeling.
Great talk, Frederick. I have 2 questions. First is, it's more of an optimization problem of where you want to install new mermaids. Do you have regions around the world where you would want more mermaids with a better model?
Yeah. Look at the map, right? Honestly, we want to be everywhere. I was just in there, and they put 8 mermaids that I can't show you because of the firewall. But they're interested in local seismicity, and so that's the next place because somebody bought some and they put them out, and that's where. I know where I'm going next to answer your question. We're going to the Atlantic. Okay, we're going to try and cross the Atlantic with about 30 new instruments in the next few years. And the reason to go there was somebody was willing to, go along with it. And the motivation there is, look, the Atlantic is surrounded by passive margins, no active subduction, no prominent plumes. A mid-ocean ridge, of course, in the middle, but this is a sort of subduction-free part of the Earth. And there has been very little seismic data collected there ever. And for the same reason that we're now looking at it, we're like, well, nobody's done anything there, so let's go there next. But the Earth is big, and the ocean has had multiple ocean bottom deployments, but there's a few instruments here and a few instruments there. Many of them, data not so good. Data don't even come back sometimes. It's the best people can do, but it's not good enough yet. And so I'm really not dissing ocean bottom seismometry. It needs to happen. I'm also certainly enthusiastic about people doing distributed acoustic sensing over the ocean. So the passive telecom cables that people are now looking for turning into seismic records. That's happening, that is going well, but that's wherever there is cable already. Then there is a latest thing called smart cables that puts actual seismic instrument in between already laid cable, and that's gonna, and then in the middle of that, we'll be there with instruments that collect, 50, 100, thousands of new observations relatively cheaply, relatively fast, that will form a backbone and a, starter for the work that's gonna have to come.
Thank you. Quick follow-up. Is there any interest in having these mermaids around cold regions such as Greenland or Antarctica, which can hear these big calming?
Yes, there are. And so the number one question is, what's the latest model going to have to be? It will need to be equipped with ice-avoiding technology so that when it finds itself under an ice sheet, that it will know how to not try to come up and break its antenna off. And so that's a thing that we're definitely looking at. There are people in Norway who have expressed interest in doing work in their ocean, and their first question is how we're going to avoid the ice, and then that is going to need to be solved, and we are thinking about that, but not actively yet working on it. You can get the last question.
You seem surprised by the path that they were taking around the Galapagos, but the structure kind of makes sense with the currents.
Yeah, but so
I was wondering, when you deployed them, did you try to?
we did, but we didn't have all the ship time available to, and so it's wherever the ship goes. I never paid for a ship, is basically why.
The trajectory of the
Yeah.
jets?
And it's the same with the Pacific, it's it's going to go roughly that way, and there it is. And we look at Argo trajectories, and we ask, if we put a January 10th mermaid in there, where would Argo have gone if we look at its, so many years of experience? And then we do hope for the best. We don't really control it, and that's another argument to say that, we need hundreds of them. And we really want to get back with the oceanographic community because we show we can be done. And maybe that's my last message, right? So because they didn't listen to us, we are now doing their observations for them. So this is a CTD from Seabird that is, this is the latest instrument that goes down to 4,000, and we're literally building one for 6,000. And we are going to, with a little luck, leave deep Argo in the dust because it's not working so well, and this actually is working. But somebody's going to have to pay for it. Wow, it's like a funeral out here. Quiet.
Okay?
It's just Coca-Cola.
Is any you need tissue somewhere? So you found you don't have that. So you found your mermaid records so many volcano, right?
Yeah.
So many volcanic activity.
Yeah.
But I didn't really talk too much about that itself, and I was just wonder, have you ever think about to do some sort of machine learning data simulation? Just trying to, I don't know what you're gonna get, but I sometimes go to AGU and hear see people doing some of that kind of work and try to figure out, do a calculations.
On what? What do they calculate?
They're trying to see the eruption frequency or something that is, to do a big data set of study. We are not sure. I mean,
So-
not sure what we're looking at, but but doing that you can find some hidden pattern maybe.
So, yeah, we only really have one mermaid with continuous data. Actually, we have two now.
Okay.
We hope to get more.
I see.
Here's what I know people want to know, and I'm interested in if we can deliver that. What is basically even the fraction of submarine to subaerial explosion? I hear people in terms of Earth evolution are not sure how many submarine volcanoes actually erupt because you don't know it.
Yeah, we don't say it, right? Yeah.
And
it's
so
right, yeah.
we deliver all these data, but you know, that what I showed was looking, and then we went and got all the data.
I see.
If we're going to get in the Atlantic not good earthquakes, which is possible, maybe we'll be trying more volcanic. And your real question, as people shown what to expect, I haven't seen that, but I'm getting more and more calls from volcanologists who are saying, oh, wonder if we can put them some places. I'm like, yeah, be my guest, because we you know, this is technology and it's going to be used for some.
So to retrieve the data, it takes money.
Say it again?
To retrieve the data, it takes money.
It takes money because you pay for a bandwidth. Kurta, how are you? Thank you for coming. Good to see you. Happy and healthy. Hello, I'm Frederick. Nice to meet you.
She is a student